Hello, my dear students. I am Professor R.V.S.S.N. Ravikumar.
Dive into the fascinating world of quantum electrodynamics, starting with the transition from classical light particles, photons, to quantum bits, and then deriving the full Hamiltonian in the radiation field. Let's begin. See, when we study radiation, we move from classical wave equations to localized quanta called photons. In quantum computing, we represent a two-state quantum system as a qubit. Let's see how transverse electromagnetic waves propagate and how they interact with atomic states. Now, let us write the Hamiltonian of an atomic system in a radiation field. H is equal to HA plus HR plus H dash. Expanding this for an electron of charge q in a vector potential A and neglecting the small q square A square perturbation term, we arrive at our interaction term H dash is equal to q by m into E dot P in the Coulomb gauge, where the divergence of A equals 0. This is a very elegant result. Next, we quantize the radiation field. In this section, we describe the electromagnetic field in terms of the number of photons in various states. By separating variables A of r, t equals A of r q of t, we obtain the 3D wave equation. We introduce dimensionless variables and represent the Hamiltonian as a sum over mode field energy. HR is equal to sum of n plus half h bar omega. The eigenstates represent the number of photons. To visualize these complex interactions, Richard Feynman introduced graphical diagrams in 1949. Look here carefully. A wavy line represents a photon, and a solid directed line represents a fermion, like an electron or positron. A QED vertex is the point where a photon and two electron lines meet, governed by Dirac gamma matrices. These form the fundamental building blocks for visualizing pair creation, pair annihilation, and scattering. Finally, we explore key scattering processes. In the classical limit, we have Thomson scattering, where light scatters with no change in frequency. But quantum mechanically, Compton scattering causes a wavelength shift. The shifted frequency is given by the Compton relation. For electron-electron scattering, we have molar scattering, which exhibits symmetric properties under tossing symmetry. Let us summarize this lecture and remember, physics is all about understanding the deep symmetries of nature.